Hi, this video contains solutions for some problems from Chapter 10, problems in particular about calculating rotational inertia. And number 36, they have given us a picture of a disk and rotate around, that's where its axis is, and then we're moving the axis to different locations, h, away from the axis. And they also gave a graph. And I don't think we're going to need more than just two values from the graph. So we know when the rotational inertia, when the h distance, I'm looking at the graph here, when the h distance is 0, in other words, when it's actually rotating through the center of mass, that the rotational inertia is 0.050 kilogram meters squared, and when it's rotated a shift of 0.2 meters, then the rotational inertia we would expect to increase, and indeed it is bigger. And they want to know what the mass of the disk is. Now this is a disk, so we know that the rotational inertia of a disk about its center of mass, disk is just like a really flat cylinder. It's 1/2 mr squared, where r is the radius of the disk. They haven't given us what the radius of the disk is, but I think that will be okay without knowing that. So I know that this here is equal to 1/2 mr squared, and this is equal to 1/2 mr squared plus the mass of the disk times the shift squared. Right? This is the parallel axis theorem. And since we have values for these two, I think we should be able to solve for the mass, right? In fact, I think the easiest way would be to recognize that this expression here, since I know that that's equal to 0.05 kilogram meters squared, I can just substitute that here. So making that substitution, I have 0.15 is equal to, that's equal to 0.05 plus the mass times 0.2 squared, and there we go. We have an equation with just m in it. So that's 0.1 is equal to m times 0.2 squared is 0.04. So the mass is 0.1 divided by 0.04, which is the same as 10 divided by 4, or 2.5 kilograms. Right? Number 38. In this one we have an axis with a thin rod of negligible mass. What does that mean? That means if it has negligible mass, it means we can ignore any effect that the rod has on the moment of inertia. In other words, the moment of inertia is just because of these three particles. So the total moment of inertia, or rotational inertia, of this assembly is just the mr squared of this plus the mr squared of this plus the mr squared of this. It's just like three particles. The rod has negligible mass. So even if you tried to calculate it, you'd have to put in 0 for the mass, right? And the mass of each one of these is 0.01 kilograms. And the length of the rod is 6 centimeters. And I think they are evenly spaced, right? Yes, if those distances are all d, so this is 0.02 meters so is that, and so is that. So the total moment of inertia around that axis is just m. Then the r of the first particle will be 0.02, and then 0.01. The r for the second particle will be 0.04, and then 0.06 for the third particle. That's the total. So why don't we just put a number on that? So let's see, that's 0.01 times, so I'm just going to factor that 0.01 out, and then I have 0.02 squared plus 0.04 squared plus 0.06 squared. So that's 5.6 times 10 to the negative fifth kilogram meters squared. You see that there? Just barely. All right, and now they would like to know if they remove one particle, that is 33% of the mass, by what percentage does the rotational inertia of the assembly around the rotational axis decrease when the particle removed is the innermost and then the outermost? So if we remove the innermost, I'll put a little line through that to indicate that I'm removing the innermost, then I don't have that anymore. I just have these two. So let's see what it would be then. Let's bring that same expression back up and delete that first one. So now it's 5.2 times 10 to the negative fifth kilogram meters squared. And if I remove the outermost, then the total rotational inertia will look like that. And I can get that, just change this one to 2, and that is 2 times 10 to the negative fifth. And they want to know by what percentage does it decrease. So percent change is just the difference between these two divided by what we started with. So the difference between these two is 0.4 times 10 to the negative fifth divided by 5.6 times 10 to the negative fifth. So for part A, that's a 7% decrease. And part B, we go from 5.6. Sorry, you notice that I dropped the 10 to the negative fifths because when I divide those will just cancel out. You could leave them in, you get the same thing. I'm going to do the same thing here. I'm basically going from 5.6 down to 2, so that's a decrease of 3.6. Oops. 3.6 out of a total of, 0.6 out of a total of 5.6. And that's a 64% decrease. So what's the point of all that? I think the point of that problem is just to look at the difference that it makes. We're removing the same amount of mass in both cases, but how much the position of that and its distance from the axis influences how much that particle adds to the rotational inertia. So that outermost particle really adds a lot, right? It adds a lot more. And likewise, this innermost particle adds little compared to how much those add because of those r squareds in there. Right? So make sure you can see all that. All right. number 40. Let's see, we've got an arrangement of 15 identical disks that have been glued together in a rod-like shape of length 1 meter with a total mass of 100 milligrams. Disk arrangement can rotate about a perpendicular axis through the central disk. What's the rotational inertia of this arrangement? And if we approximated the arrangement as being a uniform rod, then what is it? So, in part A, we're going to actually find the rotational inertia. So I have a bunch of disks, but then most of them are offset from the axis. So this is one side, if this is the axis here, and then I have the same thing on this side. 1, 2, 3, 4, 5, 6, 7. So I have 15 different things I have to add together, 15 little disks. All right, so let's see if we can do that. And each one of them has a mass, they have a total mass of 100 milligrams. So that means each one of them has a mass of, 100 milligrams. That's 1/10 of a gram, which is 0.0001 kilograms. Right? That's the total mass. So each one of them has a mass of that over 15. Right? 1/15 of that. Okay, so let's see if we can do this. The first one, and the length, sorry. The total length here is one more little calculation, quick calculation we have to do, is 1 meter, which means the radius of each one. There's a diameter, a diameter, a diameter. There's 15 diameters or 30 radii going across here. So that means the radius of each one is 1 meter divided by 30. That's what the radius of each one is, 1/30th of a meter. Okay, so the total rotational inertia, the middle one is actually a disk rotating about its center. So that's 1/2 times m times r squared. This one and this one are both shifted the same distance from the axis, and you can see that they have been shifted a distance of 1 diameter, or 1/15 of a meter, right? It's been shifted 1/15 of a meter, 2 of those radii. So that, there's 2 of them, so I'm just going to put a 2 here. That's going to take care of both of these, and then both of these will be the same, etc., all the way out. So this is kind of a tedious calculation, but it's not hard. Okay, so the mass of this one is the same, 0.0001 over 15 times 1/30th squared. That's the, and it's a disk, so there's a 1/2 there too. So that's the same expression as this. That's the 1/2 mr squared. And then parallel axis theorem, I have to shift m, and then this shift is 1/15 of a meter squared. Right? Plus, I've got 2 more disks where I've got the same 1/2 r squared. That's always going to be the same for all of them. Plus, now I'm out to these disks. So how much is that shifted? That's shifted from here, the rotational axis, to the center of mass here, so that's 2 of those diameters, or 2/15. Right? Sorry, I should put that term first. Let me do that first. 0.0001 or 15 times the shift squared right plus next ones. So let's see, I've done those, now up to this one here. 1/2 mr squared plus m, and now I'm shifting 1, 2, 3 diameters, or 3/15 squared, and then you get the idea. It's going to look like this, same thing, with then a 4/15 and a 5/15 and a 6/15. So which is the one I just did, this one, right? So that's 4, 5, 6/15. So same thing, except this is going to be 4/15 squared, and then same thing, except this is going to be 5/15 squared, and then the same thing, this will be 6/15 squared. So that looks like fun to calculate. Let's see if we can get that all in the calculator without messing it up. There are some things we could factor out. I wonder if we want to even mess with that. Trying to think of the easiest way to do this. I think that what I'm going to do, I don't know if you know this trick or not, I'm going to store this number into my calculator with that 0.0001 over 15. That number comes up a lot, right? That's the mass of one of the disks. So I'm going to store that in my calculator. Here's the store button right here, right above the on button. Store. I'm going to store that as x. And now every time I hit x on my calculator, it knows that I'm talking about that number. So that's going to make things a little bit easier. Alright, so let's try it that way. So I have 1/2 times the mass times 1 over 30 squared. The 1 squared is just 1, so I don't have to worry about that. Plus 2 times 1/2 m times 1 over 30 squared plus m times 1 over 15 squared. That's that one. Plus 2 times 1/2. You know what I should have done? Well, whatever, it doesn't matter. I was thinking I should have just stored that whole thing as x, but it doesn't matter. I'll just finish doing it this way. X times 1 over 30 squared plus m times 2 over 15 squared. I had to put that whole thing, the denominator is not 1 anymore, right? So that whole thing had to go in parentheses, plus 2 times 1/2 m times 1 over 30 squared plus m times 3 over 15 squared plus 2 times 1/2 m times 1 over 30 squared plus m times, am I at 4/15 now? 4/15 squared plus 2 times 1/2 m times 1/30 squared, which is the same as over 30 squared, right? Plus m times 5/15 squared plus, last one, 2 times 1/2 m over 30 squared plus m times 6/15 squared. I sure hope I got that in there right. All right, and if I've done that correctly, this whole thing is equal to 5.44 times 10 to the negative 6 kilogram meters squared. And looks like we did not do it correctly. Great. Super. Well, you know what? I think that I'm not going to do it again because that's just a waste of video. The book does not have that as an answer. So if you were following along there and you see what I did wrong, then I hope you can fix it. But the point of this problem is that if you get the correct value for this, which that is not, then they suggest, instead of doing this craziness, what if you just approximate this and say, you know what, all these disks glued together, it's basically like a rod, right? It's a little bit of a lumpy rod. But the moment of inertia of a rod about its center is just 1/12 ml squared. So wouldn't that be a lot easier? That's 1/12 times the mass of the rod, 0.0001 kilograms, times the length of the rod, which is just 1 meter squared. So that's 0.0001 over 12, and that's 8.33 times 10 to the negative 6 kilogram meters squared. Oh, they have 8.3 times 10 to the negative third. That's weird. What's going wrong there, I wonder? I wonder if that's their mistake or mine. Did I mess up my conversion from milligrams to 100 milligrams is 0.1 grams, which is 0.00. No, so this is right. I don't know. I think I like my answer. So anyway, let's just presume that this is the correct, assuming that it's a thin rod. And then the difference is something like, if you do this right, I think it's 8.352. So the point is, it's super close. So when we say, oh, let's just approximate that as a thin rod, it's not a bad assumption to make, and it saves you an enormous amount of trouble. Well, we'll say nothing more about the trouble we had there, or the trouble I had. So that's the point of that problem. And the last one in this assignment is number 42. Hopefully this is less tedious. So we have the masses and coordinates of 4 particles are as follows. We got 50 grams at, let's see, what do my coordinates look like, up to, what is 4, positive 4 is the biggest, or y. So that's about 4 by 4 grid should do it. So let's see what we got here. We got a particle at 2, 2, these are all in centimeters, and that's 50 grams. And I've got another particle, 25 grams at 0, 4. And I've got another 25 gram particle at negative 3, negative 3. I hope I'm reading this right. And then a 30 gram particle at negative 2, 4. That's negative 2, 4. And that's 30 grams. You do all right there, I think. They want to know what's the rotational inertias of this collection if you rotate it about the x-axis, the y-axis, and the z-axis. Suppose the answers to A, right, and then make some conclusion about the relationship of those. So we'll deal with that. The z-axis would be like rotating it like this, right? Around that z-axis is going straight into the page. Okay, so part A, rotated around the x-axis. So these are just a collection of particles. So the I total is the I for each one, and these are just 4 particles, so it's the mr squared for each one. The book sometimes does, when things are small, like grams and centimeters, instead of doing kilogram meter squared, they'll do gram centimeter squared for moments of inertia to keep the numbers more civilized, I guess. So I think I'll follow suit here. They do, in fact, do this in their answer key. So if you did yours, you can do the conversion. It just is a matter of moving the decimal several places. So okay, so the first one is, I'm going to say this is the first particle. That's m times r squared. And if I'm rotating around the x-axis, the distance from the axis, it's not the distance to the origin, it's the distance from the axis. That is 2 squared. This one has a mass of 25 grams, and it's a distance of 4 from the x-axis. That's the axis of rotation, right? If it's rotating around this, that's the distance to the axis. So it's just the y-coordinates, right? Plus 30 times 4 squared plus 25 times 3 squared. And that comes out to be about 1.3 times 10 to the third gram centimeters squared. If you did it in kilogram meters squared, that would move the decimal place. Let's see, how many places? 1, 2, 3, 4, 5, 6, 7. It would be 1.3 times 10 to the negative. I think I'm doing this conversion quick in my head, so I think this is right. Maybe that. But it would be the same number here. This would just be a different. So I think this is right. Because from grams to kilograms is going to move it 3 places. And then centimeters would be 2 places, but it's squared, so that's 4. So 3 places and 4 places. I think that's right. All right, B. What if we rotate it around the y-axis? So now the x-coordinate is the one that matters. So the 50, this one is still 2 units away from that axis. The 25 gram particle is actually on the axis, so it doesn't have a moment of inertia. The 30 gram one is a distance of 2 away. And this one is distance of 3 away. And that, if you run the numbers there, you should get that it's about 5.5 times 10 to the second gram centimeter squared. Or again, you can move the decimal 7 places if you did it in kilogram meter squared. And then in C, they want the total if we rotate it around the z-axis. So if it's rotating around like this, right, around an axis coming out of the page right at you, now the distance from the axis is this Pythagorean distance here. And remember that we're going to square that distance. So I would have 50 times, this Pythagorean distance is the square root of 2 squared plus 2 squared, but we're going to square that. So that Pythagorean, that hypotenuse, the square root sign gets peeled away by squaring, and then 25 times, and the coordinates of this, 4 and 0, and then the 30 got 4 and 2, and then this one we got 3 and 3. And the whole point of the latter part of this problem, can you see all that? Is if you look at these two things, this is 50 times 2 squared, 4 squared, and so on, and then here's the 2 squared. So here's the coordinates, the 2 squared and the 2 squared, 4 squared and 0, the 4 squared and the 2 squared, the 3 and the 3. So this should come out just to be the sum of these two. So is that 1.85? Right? And then, so part D is like, so what's happening here? It's just the sum of those. And why is that happening? It's because of that relationship with the hypotenuse, and the hypotenuse getting squared ends up just being the sum of the squares of the two coordinates. So that's kind of interesting and cool, I think.